In this video, we're going to talk about how to interpret potential energy diagrams and what information that we can get from them regarding mechanism of reactions, thermodynamics, and kinetics. So we've already discussed one type of reaction, which is acid-base reaction. If we were going to draw the mechanism of this reaction, recall that what we would do is show that a lone pair of electrons is forming a bond to the hydrogen, and this bond is becoming a lone pair of electrons on chlorine to create a molecule of water plus the chloride ion. Another kind of reaction that we haven't discussed yet is called a substitution reaction. The mechanism is very similar in that hydroxide, in this case, still is donating a pair of electrons, but instead of accepting a proton, accepting a bond to this carbon, and we're still breaking a bond to chlorine to form methanol, or a new oxygen-carbon bond, and a chloride ion. So what I want to point out in this slide is that the mechanism is the sequence of bond forming and bond breaking steps that leads from reactants to products. So let's say that we wanted to draw a potential energy diagram for the reaction that we just described. The reactants could be here. We had hydroxide and chloromethane. And the products are lower in energy in this case. So the relative energies between the reactants and the products describes thermodynamics. If the products are more stable, those are going to be favored under equilibrating conditions. If the reactants were more stable, those would be favored. This is what we described in the section on acid-base chemistry. Imagine hydroxide slowly approaching this carbon. What's going to happen as the hydroxide approaches the carbon is that the electrons in the hydroxide are going to be getting close to the electrons in the carbon-hydrogen bonds. Electrons repel each other, so that means that we're going to be going up in energy as the hydroxide ion approaches that carbon. But at some point, we're going to reach a transition state where we start forming the stronger carbon-oxygen bond and breaking the weaker carbon-chlorine bond. So now we're going down in energy until we get to the products. This point right here is called the transition state, where we go from increasing energy to decreasing energy. The transition state for this reaction would look something like this, where carbon has half or part of a bond to the oxygen, and the bond to the chlorine has partially broken, while nothing is really happening to the carbon-hydrogen bonds. So as this hydroxide gets closer to the carbon, we go up in energy till we get to a certain point where we start to form that stronger carbon-oxygen bond. Meanwhile, we're breaking the carbon-chlorine bond, so now we're going down in energy till we get to the more stable products. This is called a potential energy diagram. And as we'll see, this distance right here represents the activation energy, usually abbreviated EA for a reaction, and this distance between the reactants and the products is going to be the enthalpy, and this is going to describe thermodynamics, and this is going to describe kinetics. Okay, so before we get too carried away, let's talk about first enthalpy, otherwise known as delta H. This describes thermodynamics, otherwise known as relative energies of the reactants and the products. So we don't really care. The pathway that's taken between the reactants and the products is not important when we're considering thermodynamics. We just want to compare where we started to where we ended up and see are the reactants higher in energy or are they lower in energy. This is very easy to do if we have a table of bond energies like we have here. So if we consider this reaction and we're not worried about the mechanism. Notice that what's happening is we're breaking a CH bond and forming a carbon-chlorine bond. We're breaking a chlorine-chlorine bond and we're forming a hydrogen-chlorine bond. And so remember, all you need to know to understand enthalpy is that you have to put in energy to break bonds, and when bonds form, that releases energy, right? So in order to break this bond, it turns out we need to put in 381 kilojoules. And in order to break this bond, we have to put in positive 242 kilojoules. So the sum of these is 623 kilojoules, right? But on this side of the equation, what we're doing is we're forming a carbon-chlorine bond. When you form bonds, you're releasing energy, so that's negative 331 kilojoules. And when you form a hydrogen-chlorine bond, you're releasing 431 kilojoules, right? So the net amount of energy released here would be negative 762 kilojoules. So notice that we released more energy than we absorbed. We absorbed energy to break the bonds. We released the energy to form the bonds. So the delta H here would be minus 139 kilojoules, which means that it's an exothermic reaction. Let's say we wanted to draw a potential energy diagram for this reaction, just considering enthalpy. What we would draw, just like before, is we now know, based on our calculation, that the products, and I'm just going to write products here, are more stable than the reactants. We released energy. We're forming stronger bonds, so we're going down and downhill in energy, right? The activation energy for this reaction we calculated in order to break all the bonds. On the previous slide, we said that that's going to require the input of 623 kilojoules, right? And then we get to some transition state, at which point those atoms are going to those bonds are going to rearrange themselves and release 762 kilojoules of energy, right? So the activation energy here is the 623 kilojoules of energy that we had to put in to break those bonds. Then, from this point, we released 762 kilojoules of energy. So the change in enthalpy, the delta H, is equal to minus 139 kilojoules. This is just a difference between the energy of the bonds and the reactants versus the energy in the bonds of the products. And this is essentially a much prettier picture of what I just showed. So if the starting materials are higher in energy than the products, in terms of enthalpy, all we're going to be considering is the relative energies of the starting materials and the products. This would be an exothermic reaction that released energy. This would be an endothermic reaction that absorbed energy because the products are higher in energy than our starting material. So for thermodynamics, all we care about is the relative energies of the starting materials and the products. Are the products higher in energy than the reactants? Are the reactants higher in energy than the products? Okay, so we know that enthalpy isn't the whole story. We know this from Gen Chem, right? Delta G describes the spontaneity of the reaction. There's an enthalpy term and an entropy term, right? So if delta G is negative, that means the reaction is spontaneous. If delta G is positive, that means the reaction is non-spontaneous. For the vast majority of organic reactions, this delta S term is essentially pretty close to zero. So what we can simplify this by saying delta G is pretty much equal to delta H. So in this class, we're going to assume that delta S is negligible. We're going to ignore entropy. Just look at enthalpy. So if the bonds formed are stronger, we're going to say that's spontaneous. If the bonds are being formed are weaker, we're going to say that's non-spontaneous. Okay, so let's compare that to kinetics. What we said is kinetics is related to the activation energy of the reaction. What I'm showing here is three reactions, right? we can form diamond from carbon. That's a spontaneous reaction, meaning diamond is more stable than coal. Rust is more stable than iron. Gasoline and air mixed together is less stable than the carbon dioxide and water that form when you burn gasoline. But notice, these reactions are extremely slow under normal conditions, right? If we just take gasoline and mix it with air, nothing happens unless we light a spark. So kinetics describes how fast the products form from the reactants. It could be a spontaneous reaction, but it could still take place very, very slowly. So what we're going to say, like I said before, kinetics describes how fast a chemical reaction takes place. And remember that we said the kinetics of a reaction is related to the magnitude of the activation energy. So if we have a small activation energy, that's going to be a fast reaction. If we have a large activation energy, that's going to be a slower reaction. So how big the activation energy is going to allow us to figure out how fast a particular reaction or a particular step in a reaction will take place. Okay, so again, we can get two pieces of information out of a potential energy diagram. If we look at this part right here, if we look at the distance from the reactants to the transition state, so this is the transition state. If we look at the difference in energy of the transition state and the reactants, that's going to tell us the activation energy. Low activation energies mean faster reactions. Larger activation energies mean slower reactions. That's kinetics. Thermodynamics just describes the relative energies of the reactants and the products, ignoring how fast those things are forming. If the products are more stable than the reactants, that's going to be an exothermic reaction, and in this class, a spontaneous reaction. Luckily, for us, potential energy diagrams describe both kinetics and thermodynamics, so we can get a lot of information out of these potential energy diagrams. What if you had a multi-step mechanism? Let's say a reaction took place in 3 steps. What you're going to see is for each step, you're going to go through a transition state and get to an intermediate. So let's say, just hypothetically speaking, reactant A goes through some transition state to form intermediate B. B goes through some transition state to form intermediate C. Intermediate C goes through some transition state to form product D. So the net reaction here would be A goes to D through intermediates B and C. This would be a 1, 2, 3 step mechanism. So for each step in a mechanism, we're going to have a transition state. So the peaks of each potential energy diagram are your transition states. And for each peak, that means that we have a step. So this is a 3-step reaction. Each trough is either going to be a reactant, a product, or an intermediate. To summarize, the mechanism of a reaction is going to be the series of individual steps, bond forming and bond breaking steps that lead from reactants to products. And to illustrate those steps, we're going to use the curved arrows that we've used in the past to show how bonds are forming and bonds are breaking. I want you to be able to read potential energy diagrams and get thermodynamic information and kinetic information from these diagrams. Remember, thermodynamics is simply a fancy word that describes which side of the equation, the chemical equation, is more stable or less stable. Kinetics describes how fast a reaction takes place and is related to the activation energy of that particular reaction. So luckily for us, potential energy diagrams describe both thermodynamics and kinetics. I want you to be able to identify and use relative energies of the reactants and the products to describe the thermodynamics of the reaction. Is it exothermic? Is it endothermic? Is it spontaneous? Is it non-spontaneous? And then use the relative activation energies of different reactions to describe whether one particular reaction is going to happen faster or slower.